See, in this lecture, I will discuss this molecular speed and energy distribution. Already, I have shown you one curve for this. See this curve. So, in this lecture, I will discuss more about this curve, and I will give you one more curve for this molecular speed distribution and energy distribution, and some numericals based on kinetic gas equation and energy calculation of gas molecules, right? And mainly we will focus here for translational kinetic energy, not other rotational and vibrational. See, this molecular speed and energy distribution of gases, this is given by Maxwell and Boltzmann relation. So a simple plot, if we see between at given temperature, the plot is like this. So I'm taking it a very simple case. So here y-axis, in many books you will find some incomplete information here on the y-axis and here on the z-axis, right? Z-axis, x-axis, they will give you like energy or speed. So I am taking here speed. So what is the unit of speed here? Unit of speed is meter per second, right? Meter per second. And many times I have also told you that fraction of molecule, this area under the curve will give the fraction of molecules. So if we plot here on the y-axis fraction of molecule, so how we will get this area under the curve is equal to, see, area under the curve here should have dimensionless, must have dimensionless, then only this will give you the fraction of molecule. So basically this y-axis is, basically this is dN by Na, means fraction of molecules present in 1 mole divided by dV, right? So what is the unit for this here? Unit for this is molecules, fraction of molecules, means here we can write here molecules, and more precisely fraction of molecules into second by meter, right? So this is the unit of this. So sometime this is represented by F, right? A function F, right? So this F has the unit molecules into second per meter. So when you take area under the curve, that will give you the fraction of molecules, right? That will give you the fraction of molecules present in 1 mole. So what is the interpretation of this graph? See, if you see this region, very small molecule have this, low speed. Some of the molecules have high speed, means fraction of molecules have high speed, and maximum number of molecules, area under the curve, that will give the maximum number of molecules having the average speed, right? So this is the maximum number of molecules having intermediate, means not much high speed, not much less speed. And with this speed you can correlate energy as well, means you can say that fraction of molecules have less energy, fraction of molecules have high energy, and maximum number of molecules have average energy. Because with the speed you can correlate energy as well, because speed and temperature are related, and this temperature and energy is related. So basically this is a simple graph which represents the variation of speed or energy with the number of molecules, right? So this relation is called Maxwell Boltzmann relation, and this is given by dN by Na divided by dV is equal to 4 pi u bar square m by 2 pi RT 3 by 2 e to the power minus m by 2RT. This is called Maxwell Boltzmann relation. This is a very fundamental equation, and by using this equation you can evaluate average speed, you can evaluate RMS speed. What formula for RMS speed we have derived from kinetic gas equation, that also you can derive from here, but it is not required for you people that you are going to differentiate this and then integrate and find the answer. That is not required. You just remember those formulas, and you will get the directly question based on that. Now see what I have explained here that can be justified. This is the master formula. We can find every speed by taking this equation only, right? Now we can justify this statement that fraction of molecules have less energy, fraction of molecules have high energy or high speed, and maximum number of molecules here. See here, there are two terms which are very important at a given temperature. See, at a given temperature, T is constant, R is constant, M is the molar mass, it is also constant. So 2R, T, M, 2 pi, 4 pi, all these are constant, M is constant. So at given temperature, for different gases, you have this variable U bar square, right? U bar square. This is the variable. So and see, this is present in two different states. In two different states, right? So see, all the other factors are here constant. So we can write here it is directly proportional to into e to the power minus m by 2RT. So there are two situations here. Suppose that this value of u square bar, this is large. So if the value of this is large, right? So what will happen? This term, this is decaying, exponentially decaying term is this. So this value is very small, and if this value is very small and multiplied with this large value, again you will get the very small value. So if this is large, so the fraction of molecules having unity speed or per unity speed, that fraction is very, very less. So this is here. And second situation, this is first situation. Second situation, when this u square bar, this tends to 0, means very small. So when this term is very small and this will multiply with this, so this whole term becomes very less, very small. So you can say that also tends to 0. So see here, fraction of molecules have very small molecular speed. So these are the two situations you can justify with by observing with this mean square speed. So if mean square speed is large, so the fraction of molecules having unit speed, that has number fraction of molecules are very less. And if it is less, relatively less, then fraction of molecules have a very less number, right? So at given temperature, fraction of molecules, very less fraction of molecules have very less speed, and fraction of molecules have very high speed, and maximum number of molecules have average speed, right? So we consider average speed and RMS speed, they are close. So you can compare with average as well as with RMS speed. So dear students, this is the interpretation of this Maxwell Boltzmann distribution of speed or energy. Now we can see here this broad curve and narrow curve. Narrow curve means the distribution. If a curve is narrow, means the distribution of molecular speed is less, and if it is broader, then so the range of molecules with that speed is more, means the number of molecules are more there, right? This is the simple meaning. Now I am showing you one more important graph here, which tells about how this fraction of molecules or fraction of molecules per unit speed, they have relation with the molar mass. That is also an important graph, right? See, this is also very important graph, and it may be see see the source from where I have taken, see they have written number of molecules, but basically you have to understood like this, right? In many books you will find here it is written number of molecules, but this is basically d n by n a by dv, right? And this is speed. So see, high molecular mass gas, if molecular mass is high, then they have what lower molecular speed at given temperature. T is constant here. T is constant. So at a given temperature, this is the variation of fraction of molecules with the molar mass. So different gases if you take, so a high molecular mass gas peak is sharp and narrow, and as the molar mass decreases, the distribution or range of speed is more, so it becomes broader. Broader becomes more broader. So you can say that the fraction of molecules, I mean speed of fraction of molecules having high molar mass, they have less speed, and less molar mass gases have more speed. So the relation between this molecular speed and molar mass, that is inverse relation. So this is I mean about the distribution of speed, molecular speed or energy. In place of speed you can write energy, and when you write here energy, then you have to write here dN by Na by E here per unit energy, right? So the similar graph and similar interpretation you have for that also. Okay, so this is very important point, and this is the Maxwell energy distribution law, right? Now let's do some practice and some questions. See, this question is based on the calculation of pressure, right? Without, using equation of state or Boyle's law or Charles' law. So this, question is basically based on the kinetic gas equation, right? So calculate the pressure needed to confine this number of gas molecules, each with mass of this kilogram, right? And URMS speed is given this meter per second in a 1 meter cube container, right? So now see what formula we can use here, and also calculate the temperature. So first we have to calculate the pressure, after that temperature. So PV is equal to 1 by 3 small m into n U bar square, right? So this is the equation. Through this we can calculate the pressure, right? This is the equation. Now see what is given. Capital N is given. Capital N is equal to 1.0 into 10 to the power 25 molecules, and small m is given. Small m is 1.0 into 10 to the power minus 25 kilogram. It is given, and U RMS is given, that is 1.0 into 10 to the power 3 meter per second. So we can calculate U bar square. This is equal to U RMS square. So this is equal to 1.0 into 10 to the power 3 square meter square per second square, right? And volume is given, V is equal to 1 meter cube. 1 meter cube. I think all the units in the SI system. So if you put all these values here, you will get pressure in Pascal, right? Pressure in Pascal. So now see, P is equal to small m 1.0 into 10 to the power 20 minus 25 kilogram, and n 1 into 10 to the power 25 multiplied by 1 10 to the power 6 meter square per second square, right? and by 3 into 1 meter cube. 1 into meter cube, right? So see here, meter square and meter cube, this is cancelled, meter is left. So kilogram, uh, here kilogram and 1 meter cube, okay. Second square, kilogram per meter per second square. So on calculation, you will get C 10 power 25, 10 power 25 cancel. So this is 10 to the power 6 by 3, right? 10 to the power 6. So this is equal to 3, 3, 3, 3, 3, 3, 1, 2, 3, 4, 5, 6.33 kilogram right. So this is the I mean you can say Pascal or 1 2 3 4 5 3.33 into 10 to the power 5 Pascal. So this is the pressure, right? Answer. Now, now see, also calculate the temperature. Now you are free to use PV is equal to nRT. Now you have calculated pressure. You have number of molecules, so you can calculate the number of moles. You have volume, and now you can calculate the temperature. So temperature we can calculate T is equal to PV by N into R. So pressure is 3.33 into 10 to the power 5 kilogram meter minus 1 second minus 2, and volume is 1 meter cube divided by n is equal to 1 into 10 to the power 25 divided by 6 into 10 to the power 23. This is per mole. So this is Avogadro's, the unit of Avogadro's number is per mole. So here this is mole, and R we can use 8.314 joules per mole per degree Kelvin, right? So per mole and moles cancel, and joules is equal to, we can write what, Newton meter square per second square, Newton meter square per second square, I think. So Newton meter square, so this kilogram meter square per second square. So all these units will be cancelled out, right? So we will get what? Multiplied by 6, multiplied by 6, and and divided by 8.314, this, so 2405, 2405, so this is equal to 2405, right, Kelvin. So this is the answer, right? So in this way you can calculate pressure and temperature, right? So this is a simple question. The you should careful about the units and other parameters when you are putting in the equations, right? Now see, this is homework, and nowadays nobody is posting the, I mean, homework uh, in the group. Nobody is I mean posting. I don't understand why all of you are not I mean doing the homework, right? So everybody should do this homework and properly post the answer and solution on the group, right? So this is the homework question. The pressure needed to confine 1 mole of N2 molecule to 24.8 liter is 1 bar. Pressure is this time given. Calculate VRMS and temperature for this sample. So this is a simple question. Now you have to calculate and post the answer on the group, right? Now see one more question. A wall of a container is struck at 90 degrees Celsius by this nitrogen 10 to the power 23 nitrogen molecules each second. What is the total force that the molecule exert on the wall if the speed of the molecule is 450 meter per second? Calculate the pressure if the area of the wall is 10 centimeter square. See, we can write here the force exerted by the force exerted by exerted by one molecule is by one molecule uh, or n molecule we can take. Okay, one molecule is related to the change change of momentum of momentum momentum in 1 second, change in momentum. So we know for one molecule we have formula change in momentum per second, right? So dp by dt, dp by dt. So in this question, in 1 second per second, in each second it is given. So in 1 second, in 1 second, 1 second, the force exerted by the force exerted by n molecules, n molecules is F is equal to force is equal to n d of mv by dt, and all we are knowing that dmv is equal to 2m into v by dt, right? So where n are the number of molecules, and, and 2 mv is the net change in the momentum of the wall, right? So now you can solve this. Put the value of n is 1 into 10 to the power 23 into 2 into mass of uh, one molecule, nitrogen, what nitrogen molecule. So mass of one molecule is, you have to take this value in kilograms, right? So 2 into 28 into 10 to the power minus 3 kilograms per mole, right? Divided by, see this, divided by 6.02, or you can take 6 into 10 to the power 23 per mole, right? So now this is the mass of one nitrogen molecule multiplied by 450 meter per second, 450 meter per second, and dt is 1 second, right? So from here you can calculate the force, and this force is coming 4.2 kilograms meter per second square is equal to 4.2 Newton, right? So this is the force exerted by this molecules striking per second perpendicular to the wall, right, with this speed 450 meter per second. Now pressure P is equal to F by A. So F is 4.2 Newton divided by area is 10 centimeter square. So 10 centimeter square. So this is equal to 10 to the power minus 2, right, meter square by centimeter square. So this is cancelled, and we'll get 4 to this is square, right? So 4200 Newton meter is equal to 4200 Pascal. So this is the pressure. This is the force, right? So in this way you can calculate the force as well as pressure exerted by the gas molecules, right? Now see, calculate the VRMS for neon gas. Another question: neon gas at 10 Kelvin. Is this value is dependent on pressure of the gas? So the answer is no, because you know VRMS is equal to 3 RT by M. So it is independent of pressure, right? No way of the dependency of this VRMS on the pressure, right? Because you know if you see the equation PV is equal to this see, in this equation if you can argue that okay, here this is what VRMS basically, if you take under root of this, so here pressure is there in the equation. No, don't be confused that this will depends on pressure. When you change the pressure, volume will change, so the product of P and V is constant. So this will depends mainly on temperature and molar mass of the gas, means mass of the gas, right? So is this value is dependent on the pressure? The answer is no. So answer of this part is no. It is not dependent on the pressure. Okay. So VRMS. So VRMS is equal to VRMS is equal to under root 3 RT by M per mole, right? So per mole. So see, quantity is not given here, so you have to take uh, what obviously you have to calculate for 1 mole of the gas, right? Not for 1 molecule of the gas. See, 3 value of R is 8.314 joules per mole per degree Kelvin into 10 Kelvin divided by molar mass nitrogen neon. So for neon it is 20 into 10 to the power minus 3 kilograms per mole, right? So this per mole cancel, per Kelvin cancel, and joules, what we can write here, joules. So we can write kilogram meter square per second square, kilogram meter square per second square, right? So this joules, in place of joule we can write kilogram meter square per second square. So this kilogram and kilogram cancel, so you will get the value in meter per second. So what we will get, approximately we will get 111 meter per second. So this is the answer. So the only point is here in this such type of calculation, unit of molar mass. See, molar mass in the text I have already told you that whenever you take this formula you should put the molar mass in kilograms per mole, right? So this is per mole, and if formula is asked what is VRMS per molecule, so VRMS is equal to under root 3 kT by small m, right? This is per molecule, So in this formula, K is equal to R by Na, Avogadro's number, Boltzmann constant, and now this small m is called mass of one gas molecule. So in this way you can calculate RMS speed per molecule, right? So this is the way how to calculate RMS speed or most probable speed or average speed if temperature is given. Temperature and nature of the gas is given. Okay. Now see another question. How much energy is needed to raise the temperature of argon from 0 degree Celsius to 25 degree Celsius? This is the first part of the question. By what ratio is the VRMS increased? Is this the same ratio by which the average translation kinetic energy is increased? So in this question, you have to solve this question in three parts. First part, how much energy is needed to raise the temperature? So we can first we can calculate this. So delta E translational energy required, average translational kinetic energy it is required is equal to 3 by 2 R into delta T, right? So if you want to raise the temperature from 0 degree Celsius to 25 degree Celsius, by assuming that this energy is not consumed in any other way, so this formula you can use. So this is equal to 3 by 2 R is 8.314 joules per mole per degree Kelvin, right? And delta T, so you can directly take here 25 Kelvin because no need to calculate once you take the difference. So basically difference is equal at degree Celsius and Kelvin scale. So directly you can write 25 Kelvin. So if you solve this, so you will get 312 joules per mole. 312 joules per mole. See, Kelvin, this Kelvin cancel, joules per mole. So this is the energy of energy required to raise the temperature from 0 degrees Celsius to 25 degrees Celsius for 1 mole. See, there is nothing is given in this equation regarding the quantity. So nothing is given so far 1 mole. This is a default calculation. So this is the E translational. Now see VRMS. So VRMS at 0 degrees Celsius by VRMS at 25 degrees Celsius is equal to, we can write 25 to 0, it is better to take 25 to 0. So 25 degrees Celsius and here 0 degrees Celsius. So this is equal to 298 by 273, right? Kelvin to the power 1 by 2, because other things are constant. Gas is same. So this will equal to 1.04. Similarly, E translational delta E or E translational at 25 degrees Celsius by E translational at 0 degrees Celsius is equal to 298 by 273, right? 3 by 2 r, 3 by 2 r, this is constant, so this you can directly write, and this is equal to 1.09. See here square root and here direct relation. So this is the factor through which energy increases, and this is the speed, RMS speed increases. So is this the same ratio by which average energy average translation kinetic energy is increased? The answer is no, right? So the third part, this is the first part answer, this is the second part answer, and third part answer is no, right? Both have different value. This is the square root and this is the normal ratio, simple ratio, right? So in this way you can calculate translational energy and RMS speed, most probable speed, and average speed.